So next here we're going to look at radiation and electromagnetic waves. Now this kind of discussion sort of focuses a little bit more on some of the different forms of heat that we're not necessarily going to talk about in this that we're not going to focus as much on in this discussion. So the only ones that really kind of apply from a superficial perspective are the infrared lamps and the ultraviolet lamps, which really don't get used a whole lot in therapy anymore. There is some small use, but not as much. The rest of what this will apply to are things like ultrasound and diathermy, which we'll get into in much more depth a little later on in the semester. So we're looking at the science behind radiation and some of the differences. We're going to talk about things like wavelength and frequency and what the significance of that is. So in looking at electromagnetic waves, some of the things to take into consideration, first look at the difference between, so all electromagnetic waves have wavelength and frequency. So to kind of define wavelength and frequency and see the relationship that they have, the wavelength is the distance of one repetition of a wave. So when you look at the picture here, you can see first of all where the crest and trough is. So you see the crest of one to the crest of another is the wavelength, whereas the frequency is the rate of passage of the crest, and it's expressed in cycles per seconds or hertz, which should sound familiar. When we talked about we were briefly going over ultrasound in lab, we talked about megahertz being the measurement of the frequency of the ultrasound. So you see, what you see here is the inverse relationship between wavelength and frequency. So the longer the wavelength, the lower the frequency, whereas the shorter the wavelength, the higher the frequency. So you can see that illustrated in the picture here. Now as we kind of go through, what you'll see is kind of the electromagnetic spectrum and the significance of how wavelength and frequency impact some of these electromagnetic forms of energy. So when we're talking about the idea of electromagnetic waves, so basically radiation kind of produces energy as electromagnetic waves, and it takes many different forms, and the amount of energy present is going to be based upon the wavelength and the frequency of the individual objects. So the illustration here, which is also in your textbook, shows an electromagnetic spectrum, and it shows the various types of waves. So you see all the way on the one end you have what is the frequency of, say, an AM radio. Again, electromagnetic energy is electromagnetic energy, whether you're talking something as it relates to a modality or something like an X-ray, like a diagnostic tool in medicine, versus a radio wave. They're all electromagnetic waves. What kind of differentiates the amount of energy that gets produced is based upon what the frequency of it is. So when you look at the spectrum here, you go all the way on the low end of an AM radio, all the way up to something of much higher energy like an X-ray or a gamma ray. You notice the increase in the frequency that occurs. So basically what you're looking at there, we have the amount of energy produced. So a photon is a unit of energy, and that influences the frequency. So in other words, basically, the greater the frequency, the greater the energy you're going to have. So obviously from a perspective of the impact on the body, at lower frequencies there's really obviously no value in as it relates to the type of electromagnetic energy produced. So you see again here all the way on the one end where the frequency is much higher, you see things that, for instance, like an X-ray. We use X-rays as a diagnostic tool in medicine, the energy is high enough to produce what we want to get out of the X-ray, versus something at a very low frequency. You have the AM radio. The picture up top is where it's showing the size of the wavelength. It's just kind of putting in perspective what the approximate size of the wavelength is. So, and you see all the way, for instance, they equate the frequency of the AM radio to basically being the size of a building. So a very long wavelength there, which is going to produce a much lower frequency, whereas all the way on the other end of the spectrum you have something, the wavelength the size of an atomic nuclei, which is very, very small, but because of that you get a much greater frequency. So that basically means that there's much more energy there, which again in the situation of an X-ray allows the energy, for instance, to pass through your body and create the image that we get. So again, it's important that you kind of understand this, and again, as we get into some of the different forms of heat that penetrate deeper, this will all kind of be much more applicable versus a lot of the different types of heat that we're talking about now. So as we talked about photons being a unit of energy in some of the previous points in the discussion, anytime that energy comes in contact with something, one of four things or a combination of the four things occurs. The energy is either reflected, refracted, transmitted, or absorbed. So as you see in the illustration, which is also depicted in your text, we have kind of what goes on with each one of these things. So obviously with reflection, as a wave hits something, it bounces back. There's no penetration, and the angle of reflection just kind of depends upon which the angle in which the energy was kind of taken to the area. If something is refracted, that means that the wave is bent as it's going through. If something is transmitted, that means it's able to penetrate the object. And if something is absorbed, that's when the energy, for instance, in what we're doing now, so when we apply a heating modality, we look for absorption, because that's going to be when the energy actually gets turned into heat. Okay, so again, some combination of this will occur when you're looking at energy, in the case being heat, is going to happen. Again, obviously the main goal that we want, particularly for the target area, is for the energy to actually be absorbed. Now, looking at the thermal effect of electromagnetic waves, again, remember we're looking at electromagnetic currents that are going to basically convert electricity to heat. So again, typically what we're seeing with this is a lot of our deeper heating modalities. So from an application standpoint, a little different than what we're going to be really focusing on here, but this is where kind of these topics get covered in depth. So when we look at how the body is going to kind of respond to this and how heat is going to be produced. So the heat produced by the electromagnetic energy is going to be proportional to the square of the current strength. So basically the increase in the strength, the increase in the heat, and the resistance of the conductor and the duration of the passage of the current. So basically, if the conductor, which is actually going to be the area that's basically conducting the energy, as the resistance of that increases, and also as the time that it takes, or the amount of time that the current is actually passing through the area, that is going to increase the amount of heat. And that's what is known as Joule's law, as described in your book. So that's going to kind of dictate how much energy gets produced and how much heat gets produced. The other thing to kind of note is that the electricity that's going to flow in regards to this type of energy looks to go through the path of least resistance. So all body tissues kind of have different amounts of resistance. So in other words, what you're going to find is that the electrical current is going to look for body tissue that is going to be able to conduct this energy. So it's not necessarily that the body tissues with higher resistance per se are going to heat up the most, because in the body, the electrical current is going to look for tissue that can actually allow the electricity to flow through a lot easier. So some of the laws as it applies to radiation application. So again, it's important to know these definitions and kind of what they mean. So the inverse square law basically means that the intensity of the radiation is inversely proportional to the distance squared. So if you really want to make this simple, basically what you look at is the closer the object is that's providing the energy, the more energy is going to be produced. But what it kind of points out, the reason why it's called the inverse square law, is that, for instance, if you decrease the distance by half, so if you have some type of energy source and it's a certain distance from the body, if you decrease the distance by half, the intensity actually increases fourfold. So in other words, you don't just look at, it's not just a direct proportion of getting the object closer and that's how much energy gets transmitted to the body part. It actually increases by more than that. So again, the basic premise here is that the closer the source is to the body, it just increases the energy that much more. So, it's important. So, for instance, your book talks about the example, again, of an infrared lamp, which doesn't really get used as much in therapy anymore. But if you were to use an infrared lamp as a heating source, if you move it closer to the body, the more energy gets produced, but it's much more than just the individual distance. The cosine law looks at an optimal angle. So, in other words, the most optimal angle for absorption of the energy is going to be a perpendicular angle. So if you look at the illustration pictured here, as the radiation angle is at 90 degrees, so it's perpendicular, most of that energy, if not all of it, is going to be absorbed. Whereas you change the angle, you only get a smaller amount of energy getting absorbed, and the rest of it will actually reflect off of the body part. Okay, so if you kind of had to sum these two laws up and at the really most simple level, basically the closer the source is to the body, the more energy is going to be produced, and the more you apply it at a direct perpendicular angle, the more energy gets absorbed. So that's in looking at these laws as it relates to radiation application. And then two more laws as they relate to radiation application. The law of Grodish-Draper. That law basically states that for a wave to be beneficial, it must be absorbed. Okay, so in order for something to be beneficial to a specific tissue, it needs to be absorbed to produce the energy that is required. So if, in the case of a heating source that just heats superficially and can't get to deeper tissue, obviously is going to be of limited benefit to the deeper tissue. The Arndt-Schultz principle just relates to that there is an optimal amount of energy that can be absorbed. So less is not beneficial, and more can potentially be detrimental. So there's an optimal level of energy that needs to be absorbed. So again, not enough obviously isn't going to produce an effect, and there's the potential that too much can actually produce negative effects. So more of something isn't necessarily better.